reads, a 750 gram, 50 centimeter long metal rod is free to rotate about a frictionless axle at one end. So I've drawn that there. While at rest, the rod is given a short but sharp 100 Newton hammer blow at the center of the rod, aimed in the direction that causes the rod to rotate about its axis. The blow lasts a mere 2 milliseconds. What is the rod's angular velocity immediately after the blow? All right, so here's our example. This is all set up. We have our rod. Here's its axle. That's where the center of mass is, so we're going to assume a uniformly distributed rod. The mass of that rod, the length of the rod. The moment of inertia for a rod rotating about one end is 1/3 the mass times the length squared. And we know that that time is given. Now, the moment of inertia was not given to you in the problem, but that is in kind of a standard list. Remember that moment of inertia are already determined for sort of standard objects or models that can be, or objects that can be modeled as a standard object. Okay, so we're interested in the angular velocity immediately after that blow is exerted. Well, that's a change in angular velocity, right? We're going from an initial angular velocity of 0 radians per second to some new angular velocity. And what causes a change in angular velocity? Well, an angular acceleration. And of course, what causes an angular acceleration is a torque. So we're going to look at this as a torque problem, knowing that the net torque acting on the object has to equal the moment of inertia times the angular acceleration. Once we know that angular acceleration, we can think about how that angular acceleration causes a change in the angular velocity. Remember, omega final is going to equal omega initial plus the angular acceleration times the time. Okay, so how do we look at the torque? Well, we've done that process before. We do an extended free body diagram. So here's our object. Here's an extended free body diagram. We have forces acting at the pivot point, but they are along or at the pivot point, so they're not going to exert a torque. We're going to do sort of a partial analysis just to move a little bit forward. We're not doing a full static problem, and so we're just going to look at that partial. We can talk, well, maybe there's a force that direction and a force that direction. We know at the center of mass there's the force of gravity. Well, that points straight down, so that's acting along what we're going to define as the axis. But we have a force of 1,000 newtons acting in this direction. So if I set my pivot point, this has a radius equal to 1/2 L, and our fingers point, and you're going to have my backward hand, but our fingers point, they go in direction. This is our angle theta for our force. We'll call that theta force 1. All right, it will be the only one exerting a torque. So this torque is in line with the axis. So the sine of the angle, a sine of 180 degrees is 0. These, of course, is acting at the pivot point. So this is the only torque, the only force that's going to exert a torque, a non-zero torque on the object. And so we know that the torque is equal to the force times the radius times the sine of the angle. 1,000 times the radius of 1/2 L times the sine, that's a positive 90 degrees. It's going to rotate the object counterclockwise. L is 0.5, so we have 500 times 0.5, which is 250 Newton meters is our torque. Now, the torque causes an angular acceleration. Remember that the torque is equal to I times the angular acceleration. So I need to find that angular acceleration. I need alpha. So I, we know to be 1/3 the mass, 0.75, times the length, 0.5 squared, times alpha, and that's going to equal our 250. So I can solve for alpha. Of course, I don't have my calculator handy. Well, let me grab it. All right, so we have 250 times 3 divided by 0.75 divided by 0.5 divided by 0.5. We get 4,000 radians per second squared is equal to our alpha. So I'm just solving for alpha. All right, well now I know my angular acceleration, and so I can determine my angular velocity right after that blow. So we have omega final equals omega initial plus alpha times time. Omega initial 0, it's at rest to begin with. And we get omega final equals 4,000 times a time of 0.002. So times 0.002, and we get 8 radians per second. All right, so here we have a situation where we did a motion analysis to look at our angular speed at the end of that blow. That's one way to do it, but we know there's another way to do it, and that's looking at angular momentum. And we know that the angular momentum of an object is, the change in angular momentum, excuse me, is caused by that torque times the change in time. So another way we can look at this is using the idea of momentum. I know the torque, so this is W final minus W initial. Well, I know that's equal to 0. Torque times the change in time. My torque is equal to 250. Delta T is 0.002. 250 times 0.002 is 0.5. What did I do wrong? Well, these do not match. Okay. Okay, I totally screwed that up. Back it up. This is not omega. This is our change in momentum. And our momentum is I omega final minus I omega initial. It took me a minute to just think, something is not right about this. This should work. So our change, this is still 0. So I omega final is, oh, I don't know why I erased that. That was 0.5. So omega final is equal to 0.5 divided by I. So let's go back to where we calculated I. We have 0.5 divided by 1/3, 0.75, 0.5 squared. So this is the moment of inertia for a rod. And we get 0.5 times 3 divided by 0.75. And as we expect, this should also be 8 radians per second. I had to just pause the video there to figure out where I was going wrong. I got a little ahead of myself. All right, so 2 different ways we can solve for our angular speed. We can use kinematics, just like we would solve for motion, or we can use sort of a momentum analysis. Both take about the same time. There's not necessarily an advantage in this case of one over the other. We still have to determine the torque, and then we're just utilizing 2 different ideas. But what I want you to recognize is that we have all these tools. Okay, so looking at recognizing the system we have, remembering that how it's rotating depends on its moment of inertia. Reverse that. Its moment of inertia depends on how it's rotating. And then utilizing the idea of what causes that change in angular speed. The torque has to cause that change, just like a force causes a change in linear speed. All right, good job.